This is Daniel Tardin from Caliant Technologies, and you're watching Big Data at Light Speed, optical circuit switching for data centers and cloud computing networks. In large data centers, there are significant challenges, an explosion of traffic resulting from a number of sources, particularly video, mobile data, and big data. And much of this is sourced from data centers. And importantly, 75% of the traffic in the data center is actually running within the data center between clusters and racks of servers. Big data has correspondingly very big implications for data centers and networks because of the need to correlate large amounts of data between multiple databases and systems. This can lead to huge traffic loads across data centers and metro cloud networks. Big data, together with server virtualization, web applications, and the need to replicate vast amounts of data internally and between data centers, has led to a situation where there are large, dynamically changing traffic patterns and flows internally and in the metro networks. The immediate result of this is an overloading of networks with increased latency, and this leads to degraded application performance. An alternate solution is to design the network for worst-case traffic. However, this leads to a significant increase in cost at a time when we know that revenue from customers is stagnant, so it's not sustainable. The solution which does offer real value is to be able to reconfigure the network on demand to put the capacity where it is needed most. This results in a high-performance network that makes the best use of available resources. Looking at this another way, what you'll find in most data center networks today are fixed capacities with everything-to-everything connectivity. The connectivity doesn't scale to support large data flows as they arise. What is needed is connectivity and capacity where it's required, and the capability to deliver the bandwidth and the server resources needed by applications on demand. This network reconfiguration can only be partially realized with traditional packet-based switching and routing solutions. While suitable for short, bursty traffic, they can't support the switching of large data flows economically or with the low latency needed for many applications. Optical circuit switching complements this solution with the capability to economically reconfigure the network to support massive data flows with low latency and to scale as needed to 40 or 100 gigabits or beyond as needed. Let's look at a typical traditional data center network architecture, and we'll see how these factors play out. So looking at this traditional network architecture, basically what we see is bandwidth increasing 2 to 4 times per year, and importantly 75% of this traffic is east-west within the data center. Top-of-rack switch interfaces are scaling from 10 gigabits today to 40 gigabits and eventually to 100 gigabits and beyond. These factors together cause problems in the cluster aggregation layer. Basically, it doesn't scale. It has increased latency and fixed topologies that lead to suboptimal utilization of the server resources. And it's very costly in dollars, power, and space to actually scale and upgrade this network. The new hybrid data center solution combines a combination of both packet and optical circuit-based switch fabrics. So the packet-based network is designed to handle the short, bursty traffic flows between the top-of-rack switches. The optical circuit switch trunk network runs in parallel, and it switches in as needed to support large persistent flows, and it offers unlimited bandwidth and very low latency, typically less than 60 nanoseconds. Most large data flows persist for minutes or more, and so the 20 millisecond setup time of the optical circuit switch is basically irrelevant. And the optical circuit switch will expand to support 100 gigabits or beyond without upgrade. So what we have here is scalable, high capacity, low latency, future-proof connectivity. So let's look at an example of this in play. So in the starting state, All of the top-of-rack switches in this example are connected by a packet network. All of the top-of-rack switches are also connected to an optical circuit switch fabric, but only some active connections are in place on that network. And in this example, you'll see in the green lines, this is to indicate that there is active packet communication in place between the first and the fourth top-of-rack switches. So what will happen now is that a high persistence traffic flow will open up between top-of-rack switches 1 and 4, as you see by the dotted orange line. The next step is that the packet network experiencing a point of constriction notifies the management and control plane. And the management and control plane will then instruct the optical circuit switch to open up a direct optical trunk path between those two top-of-rack switches. Now the topology settles and the application now runs without congestion. Now this hybrid packet circuit switch solution makes a lot of sense, but it does need a means to control it, and this is where software-defined networking can deliver tremendous value. The key point here is that the packet and optical circuit switches can all coexist together in the infrastructure layer of the SDN model with coordinated control from the application and control layers. Let's review photonic switching technology, or optical circuit switching as it's sometimes known, what it is and what it isn't. It's important to understand in these data center applications. The first point is that it's entirely optical, so there are no OEO conversions. Most photonic switching solutions use some form of 2D or 3D optical MEMS. In Caliant's case, we use a 3D MEMS technology which we fabricate in-house in Santa Barbara. The image on the upper right shows one plane of micromirrors which can be moved by voltages applied to electrodes to move the mirrors to any desired position. To give an idea of the size of a chip containing 384 mirrors, it's approximately a 1/2 inch by a 1/2 inch square in area. The key benefits of the all-optical 3D MEMS approach are high capacity, low power, fast switching time, low latency, and very importantly, lowest cost per bit compared with switching, routing, and OEO solutions. And these features are particularly well suited to the switching of large data flows. The new hybrid data center solution, consisting of both packet and optical circuit-based elements, leverages the best of both technologies to provide a best-of-breed solution for today's data centers. Adding the optical circuit switch elements provides unlimited bandwidth and ultra-low latency for today's very latency-sensitive applications, and is also extremely well suited to the very large persistent data flows that we see in data centers today. The OCS network will also expand to support 100 gigabits and beyond in future without upgrade, making it a perfect solution for next generation data centers. Scalable, high capacity, low latency, future-proof connectivity for next generation data centers. Thank you.